Okay, today we're going over the Unit 8 review worksheet. Number 1 says give the equilibrium constant expression for the reaction below. So for that one, we just have our K sub C equals. Remember on this, we get to ignore all pure solids and liquids. So that first reactant, that only reactant there is not going to even show up in our expression here. And so we'll have the concentration of zinc times the concentration of our hydroxide. And since it has that coefficient, we'll square that. Okay, so that's it for number 1. Number 2 says which of the following correctly relates the two equilibrium constants for the two reactions below. Okay, so we have reaction 1, A plus B yields 2C. And we have reaction 2. Well, when we look at reaction 2, two things are going on there. We are reversed and we are halved. And so when we reverse the reaction, we would take the inverse of our K. And then since it's halved, we're going to raise it to the half power. And so we would have K sub C prime, our new one, would be equal to the original, 1 over the original raised to the 1/2 power. And so that would be answer D. Okay, on number 3, given the equilibrium constant K sub C for the following reaction, calculate the equilibrium constant K sub P for the same reaction at 25 degrees Celsius. And so for this one, we know that our K sub P is going to be equal to our K sub C times R times temperature in Kelvin raised to the delta N. Delta N is going to be our change in moles. And so on our reactant side, we have 4 moles of gas total. On our product side, we have 2 moles of gas. And so if we do 2 minus 4, we get a -2 for our N, our overall change in moles. And so now we just plug in what we know. Our K sub P is going to be equal to our K sub C, which they tell us over here is 3.6 times 10 to the 8th times R, which is 0.0821 latomolk, right, would be our unit for that. But I'm going to leave that off since units are not needed for K sub P. Multiply that by our 25 degrees Celsius, but in Kelvin, so 298 K. And then we'll raise that to the -2nd power. And when we get the answer, we get K sub P equal to 6.0 times 10 to the 5th. Any questions so far, Yella? Okay. Number 4, given the following two equilibria, okay, we have our first reaction here. We have a K value for that. We have a second reaction there. K value for that. We're now needing to use that to calculate the overall equilibrium constant for the overall reaction. And so remember, this is the one that's kind of like Hess's law. Okay, and so we'll have NiCO3 here, solid. It's over here. It's on the right side of the reaction. And we only have 1 mole of each, so it's fine. Okay, so I'm going to circle that just so I realize it's fine. My hydronium here, if we look at the top, we see it in that second equation, but it's on the wrong side. So let's go ahead and flip that around so it's on the right side. So I'm just going to rewrite this one. Okay, I'm going to cross that out just so we realize what we did. And then over here, I'm going to keep up with that, and we flipped it, so we need to do the inverse. because we flip. Okay, so my hydronium's good. I'm going to go ahead and circle that just so I realize it. My nickel, we have nickel on the right side, nickel on the right side, so it's fine. HCO3 is on the right side, 1 mole of each, it's fine. Water's fine. So that's all we have to do then is multiply these together, these K values, remembering that we have to take the inverse of the second one. And so we end up with our first 6.6 times 10 to the negative 9 times 1 over 4.8 times 10 to the negative 11th. And so I get an overall of 1.4 times 10 to the 7th. Any questions on that one? Okay, for this one, we have determined if the following system is at equilibrium. If not, determine which way the reaction would shift in order to reach equilibrium. How am I going to do that? What am I going to need to solve for? Q. Yeah, they give me a K. And so to see if this is at equilibrium, we're going to have to solve for Q and then compare it to K to see which shift we're going to have or if it's already at equilibrium. Okay, and so they give us our balanced reaction here. Okay, and then they give us our partial pressures of each of the substances here. And so I know my Q is going to be equal to the partial pressure of my PCl3. We have 1 mole of each, so I'm not worried about raising these to any power, times the partial pressure of Cl2. And that will be over the partial pressure of PCl5. And so then I'm just going to plug those values in since they were given to me. So I have 5 atmospheres. I have 2.7. And then I have 1.15 on the bottom. And so I get a Q equal to 11.7. Okay, and so my K sub P at equilibrium, they told me should be 11.5. And so Q is slightly larger than K. And so if we think about what that means, right, if Q is larger, it means our products were favored, right? Our products are too high. And so how are we going to handle that? Which way are we going to shift if our products are too high? We're going to shift left. Okay, so no, it's not at equilibrium. Reaction will shift left. I always put where it's going, so towards reactants. To reach equilibrium. Any questions? Okay, how number 6. 6 is the most recent thing we've been doing. This is a rice type setup. Says we place 1 gram of that substance in 100 milliliters of water. Find that at equilibrium. We have a concentration of NH3 equal to 0.045 molar. They want us to calculate K for the reaction based on that. Of course, I see I have all aqueous substances, so all of that is going to stay relevant. And then for our rice, let's just go ahead and put an R by that. For our reaction, I, remember, is your initial concentrations. C is that change that occurs. And E would be your equilibrium concentrations. Okay, and so we know, I'm going to go ahead and write what my K sub C equals over here. It's going to be equal to my Ni2 plus concentration times NH3 raised to the 6th power over my reactant. I guess it'd be a double bracket there. Okay, and so we're going to have to figure out these concentrations. And so they tell us that we have 1 gram. Okay, so I'm going to have to use that to find moles, use my size of my vessel, right, to get molarity. So I'm going to actually do that little dimensional analysis work above. So we're starting out with 1 gram of our NiNH3. Whoops. I forgot my Cl down here, didn't I? I'm sorry. Let me change that real quick. Sorry, where was I? We were here. Writing out that incredibly long thing. Okay, let me change it up here too real quick. Okay, so we have our Cl2. So we have 1 gram. So yeah, we're gonna have to do molar mass for that. And so we'll have 1 mole of that equal to 231.83. That would be grams per mole. And we have 100 milliliters as our volume, but that would be 0.1 liters, which is what we need for molarity. So we'll have 1 over 0.1 liters to introduce that liter in that we need. Okay, and so grams will go away. We're left with moles over liter, which is our molarity we need. And so we have 0.0431 molar. Okay, and so that's my initial. Okay, so scroll up a little bit. I'm going to go ahead and write that amount here under initial. I'm starting out with 0 of my product. Now be careful. I noticed on one of the worksheets that we did, they gave us an initial value for one of these. And so if they give us that, we have to use that. Otherwise, we just leave them as zeros. Go ahead.
Does that value not count?
Well, that's at equilibrium. So we're going to actually plug that in down here as we need. Well, say that again.
Like on the other worksheet, they gave us like that. So do we have to plug it into the or do we just plug in
Okay, we're going to use that. Since this is at equilibrium, we're going to be using it down here. It's not initial, it's just at equilibrium. So we are going to use that, just not yet. Okay. But if they tell us that we have an initial concentration, then we would have to use it here. Okay, so we're going to be plus x over here, plus 6x over here. And so we're going to combine those I and C's, right? So we have 0.0431 minus x here. We'll just have an x here. And then over here, we know that 6 times x is going to be equal to that molarity they gave us for that concentration at equilibrium. And so I know this is 6x, but I also know the actual value. The actual value is 0.0452. So then what I can do is just do a very simple algebra problem and figure out what x is here, okay, without having to set up a lot of work. So I know 6x is equal to 0.0452. And so I know my x here is going to be equal to 0.00753. Okay, and so we're going to be plugging in these values, but I'm going to go ahead and write down what those concentrations are before I plug them in my expression. And so I know x is 0.00753. So So that's my concentration of the nickel. That looks like a 6, so let me rewrite that a little bit. Okay, and then my concentration here for my reactant, if I do that math, I get, oh, well, I actually didn't do that for that, so we'll just skip that. Let's plug everything in. So we get K sub C equals, we have our 0.00753 multiplied by the 0.0452. We need to remember to raise that to the 6th power. And put that all over that. And so when I enter that all in my calculator, don't forget your little 6 up there, I get 1.81 times 10 to the negative 9. Yeah, what made that one different, Ashley? Sorry? No unit for K. No unit for K in this, so we're good with no unit. I think what made that one problem different is it told us we had initially some of that product in the vessel to start with, and so that's why we had to put it under the I instead of using it down at the equilibrium portion of the rice. Okay, we're on number 7. We're heating a metal carbonate. It leads to decomposition. Tells us our delta H is positive. So what does that tell us about the type of reaction this is? It's endothermic. Yeah, and so where would heat show up, or where would that energy show up in my reaction? Would it be on the right or left? If we're endo.
On the left.
On the left. So what I like to do is go ahead and put heat plus over here, because we know if we add heat, and we know how that's going to affect equilibrium, or if we take away heat, if we cool something. Okay, another thing I went ahead and did was I wrote, no I didn't. Okay, so we're going to add some BaCO3 to this, and we're predicting the effect that will have on equilibrium. So if I add this substance, if I add more, what's it going to do to equilibrium? Where are we going to go? Careful. Careful. What's it going to do? It's a solid. So will that affect it at all if we add that? Yeah, it's a solid, so that will not affect our equilibrium. So no change. Oops, that did a little wonky. Okay, so now we're going to add CO2. Okay, CO2 is a gas. So if I add CO2, where are we going to shift? Left. To relieve that stress. So we'll shift left. This is your Le Chatelier principle kind of questions. We're adding BaO. If we add BaO to our system, what is it going to do? Nothing. It's a solid again. So tricky. No change will occur. And now we're going to raise the temperature. Okay, so this is where it was important that we realize this was endothermic. And so if we raise the temperature, where are we going to shift? Right. We're going to shift right and make more product. So shift right. And if we increase the volume of the container, okay, so if we increase volume of container, what's going to happen to our pressure? Our pressure will decrease, right? And so if our pressure decreases, where am I going to shift? We have to look at our moles, right, of gas. How many moles of gas do I have on the left side? 0, right? We don't have any gas on this side. How many do I have on the right? 1. So if my pressure decreases, I'm going to move to the side with the most moles of gas. And so we're going to shift right. Good. Okay, so that's Le Chatelier. I believe that's it for the actual unit stuff. No? Well, no. Now we have some AP free responses, but they are part of this unit. So let's look at those. Okay, we have our reaction. We have a table. Wants us to, first thing I saw actually with that reaction is I see a solid. We have that carbon graphite. I'm going to cross that out. We have solid carbon, we have carbon dioxide gas, we have our temperature, we have a volume, a reaction represented above occurred. As the reaction proceeded, the total pressure of the container was monitored, and it looks like recorded here in this chart. When equilibrium was reached, there was still some C remaining in the container, and results are recorded in this table below. We see as time elapsed, how that affected our total pressure in the container at that temperature. Okay, and so the first thing they want us to do is just write out the expression for equilibrium constant K sub P for the reaction. And so we know we're going to ignore that solid. So we'll have K sub P equal to pressure of CO2. We had a coefficient of 2 out in front, so we're going to square that. And we'll divide that by the pressure of CO2. Sorry, the first one was, it should have been CO. Pressure of CO squared over pressure of CO2. Okay, that's it for that one. Okay, so just remembering to leave out that solid there. Part B, calculate the number of moles of CO2 initially placed in the container. Assume that the volume of the solid is negligible. They gave us all the information we need for that. And so what equation are we going to need to get to mole CO2? How are we going to do that? So when I read that out, that problem out, when I saw a temperature, I saw a volume, I saw it was a gas, I immediately thought PV equals nRT. Okay, and so that's what we're going to need. Solving for number of moles, we'll be solving for N. And so they tell us that our pressure is at 5 initially. I believe that was in the chart, right? Yeah, at 0 hours, right? So that's our initial pressure. So we have 5 atmospheres. The volume of that container, they told us, was 2.00 liters, so we can just plug that one in. Solving for N, our R is 0.0821 latomolk. And they gave us a temperature actually in Kelvin, so we just plug that in. Okay, and so I get moles equal to 0.105, and that would be moles of CO2. Okay, questions on that one? That was just your ideal gas law. For the reaction mixture at equilibrium at that same temperature, okay, the partial pressure of CO2 gas is 1.63 atmospheres. Calculate. Okay, so first they want the partial pressure of CO2, and so what I did there is I set up the rice, and I only wrote out what mattered in that for equilibrium. So CO2 and CO. Okay, my initial pressure, they told us, was 5.00 for our CO2. My initial pressure of CO then would be 0. Okay, so my change here would be negative x. My change here would be plus 2x. Okay, and then at equilibrium, it tells us the temperature, or sorry, the pressure. So at equilibrium, we are 1.63 atmospheres here, and we're just 2x here. And so I can work backwards and solve for x, since I know an initial and I know a final. Okay, and so I get x here equal to 3.37. And so then if I want to know the amount of CO at equilibrium, well, it's just 2 times X. So we're going to multiply that by 2, and I get 6.74 atmospheres. Questions on that one? Okay, using that, we are solving for the volume or value of equilibrium constant K sub P. So back to part A where we wrote that out. Now we're just going to plug those values in. So we have K sub P. We know the partial pressure of CO at equilibrium. It was what we just solved for. So we'll have 6.74 atmospheres. We do need to remember to square it as part of that expression. And then our partial pressure of CO2 we said was 1.63. And so I get 27.9 as my K sub P. Okay, part D, if a suitable solid catalyst were placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Justify your answer. Assume the volume of the solid catalyst is negligible. So how is that going to change equilibrium? Bingo. Trick question. Yeah, catalysts just help us get to equilibrium faster, but they do not change the expression. What's the only thing that would really change the expression, or K sub C, sorry, or K sub P? What's the only thing that would really change that for a reaction? Temperature. Yes, very good. So equal to, and so my reasoning there, exactly what Emily just said, a catalyst does not affect equilibrium. Constant. And then I went ahead and put it affects how quickly equilibrium is reached. Okay, we have another experiment involving the same reaction. Looks like our volume is the same for our container. Initially, we have 10 grams of our carbon plus CO gas, CO2 gas, each at a partial pressure of 2 atmospheres at our original temperature. So we're predicting whether the partial pressure of CO2 will increase, decrease, or remain the same as the system approaches equilibrium. So on that, let's see. We want to look at Q to help us with that prediction. And so we know Q is going to be equal to, we look at products over reactants for that. And what I went ahead and did is look at those values. So we had 2.00 atmospheres for PCO2, but we also know that's going to be squared, right? And we just had 2.00 down here for our CO. And so my Q is equal to 2. Okay, and so if we compare that to K, Q is less than K. And so what does that mean? If Q is less than K, then that means we have too much reactant. And so where are we going to shift? Right towards the products. Good. So reaction will shift right towards the products. To reach equilibrium. And we still have to refer this back to what is going to happen to CO2 when that happens. So products to reach equilibrium. And so let's think about that. If we're shifting right, how is that going to affect our pressure of CO2? Decrease. Good. Okay, and that's it.